All right, so this is our Canvas page. Hopefully we are all super familiar with Canvas by now. But yesterday I posted an announcement, so we're gonna go ahead and look under announcements, okay? And all of the announcements are listed in order that they were published in. So this is the most recent one. The most recent one will always be on the top. And I'm gonna go ahead and click on that. Okay. So the gist of this email is you want to do some test corrections. Here's some clarification on some points, okay? You need to make sure you correct all your mistakes on exam one. Please include a brief explanation on what misconceptions you had that caused the error and or what you're going to do to prevent that mistake in the future, okay? You can handwrite your explanations, you can type them, you can make a video, all of those are options, but I do want to see the corrections written down, okay? If you were one of the few people who lost points because you didn't sign your statement of integrity, like that piece wasn't clear, or that you didn't have a reference sheet, make sure that you do that for all the other exams we have this semester. And by the end of this, our course, I'll go ahead and give you those points back, okay? Those are definitely like, let's follow the rules points rather than math content points. So I just want to clarify, I understand that some of us maybe weren't clear on that, but moving forward, let's make sure that we're all writing and signing our statement of integrity and having a reference sheet, okay? Now, if there are those of you out there who are saying, you know, I don't really want to be dependent on a reference sheet, I want to make sure I know this content, you can make the reference sheet and then not use it. You don't have to use it on the exam. But I think for some of us, you know, sometimes we have some test taking anxiety or math anxiety. And so it's nice just to have, you know, a little something there that is a collection of all of your understanding of the content, okay? Here is where you might find some more useful information. So if you're like, I didn't write down the test questions, how am I going to know which test questions? If you click on this link, and I don't think you can access the link from your email. Like if you check this announcement through the email, there's no link attached. You have to go into Canvas to find the link. But this is just a document that has all of the questions for the exam, okay? I didn't label them, but for question one, the first one is A, the second one is B, the third one is C, okay? So if you're not sure which question you had, check in with me. I do have a spreadsheet that has who has what question, and so I can help you do that, especially if you didn't get a chance to answer some of the questions because you ran out of time. I can let you know which question you were supposed to have. Okay, so here's where you can access all of the test questions to help you with your test correction. So let's go back to Canvas for a moment. The last thing in here is to submit your test corrections. Please compile your work into one PDF, just like you do with the quizzes, okay? And email those directly to me at jwoo@sdccd.edu. Okay, I would like those by midnight on Sunday because we don't have school on Monday this week. Woohoo! But I'm going to do a lot of grading. So if you could get that to me by Sunday night, and then I have all day Monday and Tuesday to grade your stuff. Okay. This is also the same deadline as your homework number 3. So if you haven't started on that homework number 3 yet, make sure you get started on that. I'm happy to answer questions through WebAssign. But if, again, I'm an old lady, so if you try to email me at like 9 p.m. at night, I'm probably already in bed and I will not respond to your email. Okay, so if you want some support on that, please make sure that you reach out to me earlier rather than later. All right. I will try to have your grades updated by the end of week 4. So by the end of next week, your test corrections, all the quizzes, all this other classwork that we've been doing should be a really good estimation of where we are at our midterm, believe it or not. Okay, the end of next week is effectively our halfway through the course. I know that there were a few people who had questions on the extra credit. So the extra credit, I graded those, and I think I emailed those back to folks or put them in your Canvas with exam 1. Okay, so it's not under exam 3, it's under exam 1. So I just put everything that was for exam 1, the test and the I cannot speak this morning. The test and the extra credit all went back to exam 1. I did already include those points if you did do the extra credit. So those are already included in your test score. Okay. If you think I made a mistake, it's possible. All right. I am 100% not perfect. If you think I made a mistake on your grade, please let me know and we'll talk through it. All right. Does this clarify sort of what you need to do for the test corrections? Any other clarifying questions I can help answer? And I didn't write this in here, and I'm not sure why I didn't write it in here, but if all your corrections are good, then you earn 50% back on the points you lost. So the more points you lost, the more lucrative this test correction is, okay? So if you lost 50 points on the test, you do all your corrections, et cetera, you get 25 points back on your test. If you got a 90, you do your test corrections, you're gonna get 5 points back, right? Half of 10 is 5. So whatever, wherever you stand on this, I understand if some of you don't feel a need to do the test corrections, there's no judgment on whether you do them or not. It's more just concerning if you have a low grade and you choose not to do the test corrections. That's really where you're gonna find me emailing you a whole lot more to be like, hey, what's going on? Okay, so if you didn't do well on this exam, I would really, really encourage the test corrections. If you did fairly well and it was just like a small mistake here and there, it's totally understandable if you choose not to. Okay. I did have a few folks pop by office hours this morning for some questions. I've had people email me like, hey, here's a picture of my work. Am I in the right direction? Can you help clarify? Those are all ways in which you can reach me for support. Okay, so if you can't make office hours, you're not a morning person, whatever it is, if you send me an email that has a picture of your work and you're explaining, where you're getting confused, then it's pretty easy for me to go in, maybe write something out on my tablet and then email you back an explanation. Okay, so that's just one more layer to if you want to get some support around things. Okay. It seems like there are no other questions, so I hope I've addressed all the concerns that are out there. I'm going to go ahead and stop sharing my screen. And we're going to go ahead and jump back into the second part of 3.3. Okay. So the goal for today is to cover 3.3, 3.4, 3.5. I know it's a lot every single day, but we're going to go ahead and finish up 3.3 today. We're going to take a look at X and Y intercepts, which hopefully is familiar to us. We're going to take a look at something called extrema. All right, so we're building up a workable vocabulary for the content. And then we're going to take a look at something called end behavior. All right, so those are the last few parts in 3.3. I think today I'd like to do some breakout rooms to give you some chance to kind of practice some of the questions. I know that you all love listening to me talk for 3 hours, I know. But at the same time, I think that it's also important to, get some practice and actually try your hand at things so you know what kind of questions are kind of coming up for you before you get to the quiz, okay? So with that being said, I'm going to go ahead and change my Wi-Fi. Hold on. All right. And now I'm going to start sharing my screen for the second half of 3.3. Thanks, folks. Thanks for the confidence boost. All right. So where were we? Not yesterday, Monday. I don't see you folks every day. Where were we on Monday? So on Monday, we talked about power functions and polynomial functions. We listed all these functions in the pink that we had already learned about. And I just want to be clear on a couple things here. So you notice for the e to the x, I wrote that there's a horizontal asymptote, and the ln x, there's a vertical asymptote. So one of the things that I've seen start to come up is that some of us are assuming that these other functions, like the absolute value, the x squared, and the square root, also have horizontal or vertical asymptotes, but these ones do not have horizontal asymptotes or vertical asymptotes, okay? So only the exponential that we've learned so far has a horizontal asymptote, and only the natural log has a vertical asymptote so far. So the absolute value, the squaring, and the square root do not have asymptotes, okay? We also talked a little bit about the difference between a power function and a polynomial function. And we said that the power function really just had to be one term, but polynomials could be more than one term. What was one other difference between the power function and the polynomial function? Like, how else are they different? One's got one term, one's got multiple terms, but what else is different about them? Okay, so Ethan, I'm gonna say I like that. You can't have negative values and only integers, but we want to be clear that that refers to the power, right? So what we're really comparing here is that this power in a power function can be any real number, okay? So again, that means this part, the exponent, can be any real number. But when we get to polynomials, this power is the non-negative integers only, okay? So yes, one can only have positive values, but we're not talking about like the y value, we're talking about the power, okay? And then we talked a little bit about like identifying that, right? So which one's power, which one's polynomial, and some of them are gonna be both, like example number 2 here, okay? But what we're going to take a look at in these next few sections is we're going to focus on the polynomial function. So all the powers should be non-negative whole numbers. And what we got to at the end of class on on Monday was we looked at something called the leading term. So the leading term meant that we had to find it in standard form, Okay, so standard form means it's already FOILed. And then we line them up in order. And the degree is the power of the leading term. So if we're looking at example 6, we know that negative x to the 6th is the leading term. So that power is 6, and the leading coefficient is -1. But I want to point out one super easy mistake to make here, okay? So in standard form, we only looked at the first term. So we only look at the leading term. Okay, we only look at the leading term in standard form. But when we're in, oh no. Okay, hold on one second. Who's in the waiting room? Do you know who it is? That's so sad. I don't see anyone in the waiting room right now. Oh no. Huh. Oh no, I see her in here. Okay, you're here, yay. Aren't you glad that this is recorded so everyone can watch that? Yay. Okay. By the way, I appreciate that. Thank you for messaging me and letting me know that someone was in the waiting room. So I'm taking this one math class. Well, I'm actually taking 2 classes, but in this one class, my instructor doesn't really look at the chat window very much. And I feel like when I type a question in there and then he doesn't answer, like, I feel really embarrassed because I feel like maybe he thought my question was dumb or something, which is stupid, I know, because I just know that he didn't look at the screen, right? I know he didn't look at the chat window, but that's why I try and be really good about the chat, because I don't want you to feel like I'm not paying attention to you. But these technology issues are definitely funny. Yeah. Okay, so we were talking about the difference between standard form and factored form. Okay, so standard form, remember we said, was already FOILed, and it means that we're only looking at the leading term to answer the questions about degree and leading coefficient. Okay, so to answer this, we only look at the leading term. But when it was in factored form, okay, so when we looked at factored form, that was not FOILed. And so we had to FOIL things out to figure out the degree and the leading coefficient, okay? Now, I would encourage you to maybe try FOILing it all out for a little bit, but at the end of the day, we really just need to pick the terms with the highest powers and use those to create the leading term. Because what we're focusing on, that leading term is going to tell us so much information, and actually the other terms are going to be a little bit less important, okay? So we look to the leading term to help us answer degree and the leading coefficient. But one mistake that I actually saw on one of the quizzes that I was grading is this. So I had someone who, let's rewrite this problem. Let's say we had negative x to the 6th plus 4x squared plus 2x minus 6. Okay, so they wrote it in standard form, but then what happened was this individual said, okay, I'm going to take the 6 and the 2, and I'm going to add them together, so then the degree is 8. Okay, so here's what I think happened, and this is actually a pretty common misconception, which is why I want to spend a little bit of time on this. I think that person was thinking about factored form. And one way that you can approach factored form, I said you could like FOIL it out, but another thing that you can do for factored form is add the exponents. So for example, this x has a power of 1, and this x has a power of 1. So 1 plus 1 equals 2, and that is our degree. Okay, so I think that for that person, they thought, oh, every time I want to find the leading term, I have to add the exponents. And that's not true. Okay, so we got to be really careful about our language here. In standard form, we just pick the highest power. But in factored form, that's when we add the exponents, because that is the same as FOILing it all out. Okay, so let's just check that with 7 and 8. So for 7, let's see if this adding the powers things work. So I have a 2, I have a 1, and a 1, and 2 plus 1 plus 1 is 4. Okay, so you can add the exponents here for factored form. But if we look at example 8, that's already FOILed. So the degree is not 5 plus 4 plus 2, or 11. Okay, so the degree, I do not add the powers here. I only do that when it looks like example 7 and it's factored out. Okay, so I hope that that is a little bit more clear here, but we're going to get a lot of chances to practice finding the degree and the leading coefficient. Okay, so let's take a look at intercept. All right, so I know we already know what intercepts are, but sometimes it's useful to define it. So we know that this process works for every time we need to find an x or y intercept. So the x-intercept, the y-intercept, I think, is the easiest one to find. The y-intercept is the point at which the function has an input value of 0. That's a super fancy way of saying your y-intercept is going to be 0, comma, some number. Okay, 0, comma, some number. So anytime you're writing a y-intercept, if you get in the habit of writing it as 0, comma, a number, it's not just like, oh, my professor's really picky, she wants me to write it with a 0. What I'm trying to do is remind you that the input value is 0. So anytime you want to find the y-intercept, all you need to do is plug 0 in for the x. Okay, so that's almost like the notation helps us remember what to do. Okay, so that being said, let's go ahead and find the y-intercepts for example 9 and example 10. All right, so to find the y-intercept, all we're going to do is find f of 0. Okay, and even though example 9 and 10 look totally different, to find the y-intercept in number 10, I'm still going to find f of 0. So all that means is everywhere I see an x, I'm going to plug in 0. Okay, so 0 to the 4th, that's for example 9, minus 4 times 0 squared, minus 45. Now we want to be pretty careful with our computations here. I feel like everybody knows 0 to the 4th is 0. Once in a while, people forget that 4 times 0 is 0. Okay, so I've seen people like on a test or quiz accidentally write this as a 4, but you know it's not a 4, it's a 0. So minus 0 minus 45, which gives you negative 45. Okay. Well, we want to go back to that notation to help remind us how we even got this value. So our full answer would be 0, comma, negative 45. okay? And again, we got that by plugging in 0 everywhere we saw an x. All right. We're going to do the same thing for number 10. We're not going to FOIL it all out, okay? We're actually just going to plug the numbers right in. So 0 minus 2, 0 plus 1, and 0 minus 4. All right. 0 minus 2 gives me negative 2. 0 plus 1 gives me 1, and 0 minus 4 gives me negative 4. I multiply, I'm really careful about my signs, I get negative 8. So I write my final answer as 0, negative 8, so that I can remember that when I plug in a 0, everywhere I see the x, that's going to give me the y-intercept.
Question. Doesn't a negative times a negative equal a positive? So it's a positive 8?
Yep, sure is.
Oh, okay.
Judy. Yep. It's a positive 8. Do you like how I even said be careful about your signs? And then I was like, negative 8. Okay. So, any other very valid questions about how you find the y-intercept? So the one, sorry, Ethan, I think I missed one of your, what, are you talking about the previous section? Okay, so sorry. I'm really winning today. Telling you about how professors ignore the chat and then I totally ignore your chat. All right, so let's take a look at the x-intercept next, okay? So the x-intercept is actually a little bit trickier than the y-intercept, sometimes. So the x-intercepts are the points, and it could be one point, it could be multiple points, all right, at which the function has an output value of 0. Meaning, I don't have 0, a number, but I have a number, 0. Okay? Now, what that means is we don't just get to plug in 0 in for x, because we all know that second number talks about the y value. So to find our x-intercept, we actually have to say, take your equation and set it equal to 0. Okay, take your equation and set it equal to 0. Exactly. Yes, Laura, exactly. All right, 0 equals the equation and solve. So even though 9 and 10 are totally different looking equations, let's set it up for both of them. Okay. So in both cases, I want to say 0 equals the function. So in example 9, I get 0 equals x to the 4th minus 4x squared minus 45. And in the second equation, in example 10, I get 0 equals x minus 2, x plus 1, x minus 4. Okay, so the place where I put the 0 is different than the place I put the 0 for the y-intercept. Ooh, we actually don't even need synthetic division here. We will later on today. Okay, one of these two is easier to solve than the other. Which one might be easier? And I know easy is relative, but which one might be easier and why? What is your reasoning? All right, Ethan says the factored form. Example 10, Thea, good. All right, so I would agree, okay? And there's a reason why, even though I know how to FOIL, and I know you know how to FOIL, I did not say FOIL that out first. That actually would have made it way harder for ourselves to find our y-intercept and our x-intercept. So when you're finding your x-intercept, factored form is your friend. Okay, so if you have a polynomial in factored form and someone says, hey, I'd like you to find those x-intercepts, you should be like, yes, thank you. That is the best present that you could give me, because it means all I need to do is take each factor, set it equal to 0, and solve. Okay, effectively, someone has done all the hard work for you. So we get x minus 2 equals 0, x plus 1 equals 0, and x minus 4 equals 0. So example 10 doesn't have one x-intercept. It doesn't have two x-intercepts. It actually has 3 x-intercepts. One of them is here. One of them is here. And one of them is here. Now we should, like we did with the y-intercepts, be really good about our notation. So we're going to write this as 2, 0. That's one of the places we have an x-intercept. -1, 0, and 4, 0. 1, 2, 3 x-intercept. Yeah, we're going to take a look at what that looks like, okay? Actually, by the end of class today, we'll know how to graph number 10 without a calculator. Pretty cool. Okay, so example number 9. That one is a little bit grosser looking. Okay, we've got 0 equals x to the 4th minus 4x squared minus 45. Now, if factored form is our friend, then one strategy might be for us to say, if we could get this in factored form, then life would be better. Okay. So one of the things that maybe you learned along the way is you could factor something like this: x squared, let's do this in a different color, x squared minus 4x minus 45. Take a moment and factor that and see what you get. X squared minus 4x minus 45. So when we factor here, we want to think about numbers that multiply to make 45, but also add or subtract to make 4. Okay? So sometimes what I do is I list out all the factors. So I know it's always 1 times that number. Does 2 go into 45? No, 2 doesn't go in. Does 3 go in? 3 and 15, and then what a lot of folks are saying here, which is 5 and 9. Okay? Yeah. So of these pairs, the one that makes -4 is the 5 and 9. So we've got x and 5, x and 9. But we want to make sure the 9 has the negative and the 5 has the positive, so that we end up with a -4 when we add our inner and outer term. Okay? Now, it turns out that if you double all these powers, okay, so let's see if we can show this. This 2, right? If we double 2, we get 4. And the power with the 4x, there's a 1 here, and when I take 1 and I double it, I get 2. And then this 45 is really 45x to the 0, and when I double 0, I get 0. So this is really 45x to the 0. Okay. So if I double all the powers in the whole equation, it turns out that I can factor it the same way. Okay, so when I factor x to the 4th minus 4x squared minus 45, I actually get x squared plus 5 and x squared minus 9. Okay, so I've replaced this x with an x squared, and I've replaced this x with an x squared. That's a pretty cool extension of factoring, like with powers of 2, that you could actually do it with powers of 4, you could do powers of 6, powers of 8. So all those even powers you can actually factor very similarly to a basic quadratic, okay? Yeah, no synthetic division, yep, okay. Now, we do want to check after we factor that we factored every single part. So I think we might remember from Monday that x squared plus 5, or we had x squared plus 4, that doesn't factor anymore, okay? So this is x to the, this is going to stay as x squared plus 5. But the x squared minus 9, that does factor. That factors into x plus 3 and x minus 3. Okay. How many x-intercepts does equation 9 have? Okay. So the way we would find this is we'd set each piece equal to 0, right? We would take x squared plus 5 equals 0, x plus 3 equals 0, and x minus 3 equals 0. This one is going to give me x equals 3. So that's an x-intercept. This one is going to give me x equals negative 3. So that's an x-intercept. Ah, okay. But this last one, this is going to give us imaginary x-intercepts. That means we're not going to see them on the graph. So for example number 9, we actually only have 2 x-intercepts, negative 3 comma 0 and 3 comma 0. Negative 3 and 3. Okay. All right. So Gloria, you said you missed where that 45x came from. So just to clarify, this 45, that really has an x to the 0 power. So I was just using that to show you that you could double all the powers and get the 4th degree polynomial that we have here, okay? But we wouldn't never write it with the x to the 0. You'll always write it just as the number. It'd just be minus 45. Does that make sense? No, it was just to show you like we are doubling everything. It's just when we double 0, it's still 0, okay? Yeah, okay. So we've looked at example 9 and 10. We've seen that we need different strategies depending on the form. factored form is your friend. If it's not factored, that's when you have to do a little bit more work to make it factored, okay? Either way, though, this idea of how you find the x-intercept and how you find the y-intercept, that concept remains the same. All right, you plug in 0 for x or you plug in 0 for y. That's it. Okay. So, something called extrema. So, most polynomial functions. Okay. So, the imaginary units we will not see on the graph. And these are really excellent questions that you're asking, because when we get to actually graphing these, we'll kind of see, sometimes we only see it cross twice, sometimes we'll see it cross 3 times, and we can figure out how many imaginary ones there are based off of that. Yeah, that's a good way to put it. Okay, so most polynomial functions have something called a turning point, okay? And a turning point is the point of a graph where the graph changes direction. So the point where a graph changes from increasing to decreasing is called a maximum. And the point where a graph changes from decreasing to increasing is called a minimum. And together, instead of saying, oh, we have a maximum and we have a minimum, we call them both together extrema. So an extrema can be a maximum or it can be a minimum. Okay. So let's actually take a look at example number 9 again. Okay, so example number 9, that equation was f of x equals x to the 4th minus 4x squared minus 45. Okay, now we said that this had a x-intercept at -3, and it had an x-intercept at +3, but then those were the only 2 real x-intercepts, okay? And what we're gonna learn in a little bit is that we can actually graph this based off of what we know about the x-intercept, okay? Now, it turns out that this graph kind of looks something like this. Okay. And I think, what did we find for our y-intercept? -45. So this point would be -0, -45. Okay. Based off of my terrible sketch, how many extrema do you see on this graph? Someone says 2, someone says 3, someone says 4. Okay. So let's see. 2, 3, 4, 3. All right, all good options. Well, let's see. We have, let's see, I usually start from the left and I kind of move my way to the right, okay? And I kind of scan the graph, and along the way, I think about whether it's increasing or decreasing. So for this section of the graph, would you say that that's increasing or decreasing? Okay, we've got 1 vote for increase. Anybody else? We have 1 vote for decrease. We have 2 votes for decrease. Okay. Okay. So when we are reading the graph, I know that we drew an arrow pointing up here. okay? However, we have to read the graph the way we read English, which is from left to right. And so when we follow this graph from left to right, I think we can see that it is decreasing, okay? So here it's decreasing. What about in this part of the graph? Increasing or decreasing? Yeah, that's increasing. So let's put an I for increasing. But what that means is that at some point it stopped being decreasing and started being increasing. And that point is right here. So we can say that that is one extrema, okay? And maybe we would call this one a minimum because it goes from decreasing to increasing. What would we consider this point right here? Is that a minimum? Is it a maximum? Okay, good. Yeah, it's a maximum, right? It's the highest point in that immediate region. But we also know that after that, the graph becomes decreasing again. All right, so we're up to 2 extrema. Now I keep scanning the graph. This section is increasing, so I know I have a extrema right there. In fact, I have a minimum, okay? So this graph has three extremes. Okay. Food for thought. How do you go from 4 to 3? All right, think about that as we kind of go into that next question. Okay, Natalia says subtract 1. Okay. So let's take a look then at our other graph, our example 10. And we found that we had 3 x-intercepts, one at -1, one at 2, and one at 4. And we had our y-intercept at, we'll call this one, that'll be 0, 8. Okay. And if we were to graph this, we would find that it looks something like this. Okay, so Natalia, that might answer your question a little bit about how you could cross the x-axis more than one time. Okay. Now, how many extrema does this graph have? Okay. So let's talk about whether they are minimum or maximum, okay? So as I scan my graph from left to right, the first thing I'm gonna do is start increasing. I get to this extrema. Now, is that the top of a bump or the bottom of a bump? I think we can tell it's the top of a bump. So this point would be a maximum, okay? Not a minimum, it would be a maximum. Now, after that, the graph starts to decrease, and then it starts to increase. So as soon as a graph changes direction like that, I know there's an extrema somewhere between that decreasing and increasing. Now this one, because it's the bottom of a bump, we can say that it's a minimum. Okay, so we have the maximum at the top and the minimum at the bottom. So this function, our polynomial here, this one has 2 extrema And let's see if that matches the pattern that folks noticed earlier. This has two extrema. What's the degree of this polynomial? Ah, yes, yeah, it is 3. Now we can think about how do we get that power? Well, there's a 1 here, a 1 here, and a 1 here. So 1 plus 1 plus 1 gives me 3. This is a third degree. And if I do 3 minus 1, I sure do get 2. Okay? Just like in the first one, if I do 4 minus 3, or 4 minus 1, I get 3. So it turns out that there is a handy rule that we can use to help us understand the maximum number of turning points, okay? So if someone says, find the maximum number of turning points, or find the maximum extrema for a polynomial, you're gonna take the degree, okay? So that's why it's really important we know how to find the degree. The degree minus 1 will give you the maximum number of extrema. So if I had a polynomial that was a degree of 100, how many extrema could I have at most? 99, exactly, okay? So let's take a look at these two quick examples. Okay, we saw it on a graph, but if I just gave you this equation, x to the 4th minus 4x squared minus 45, here's how you would approach it. This is in standard form. So the degree is 4. So 4th degree. So the maximum number of extrema is 4 minus 1, or 3. It means that you could have 3, you could have 2, you could have 1, you could even have 0. But there's no way that you could have 4 bumps, or 5 bumps, or 6 bumps. Okay? And then we kind of already talked about this, but for factored form, our strategy has to be a little bit different. First power, first power, first power. I got to do a little bit of work to determine this is a third degree. And so 3 minus 1 gives me, at most, my graph will have 2 bumps. But it might have 2 bumps, it might have 1 bump, but it cannot have 5 bumps. Okay. All right, let's talk about one last topic here before we put it all together. That is one of the nice things about this section is we learn these individual pieces, but then we get to practice them again and again because they're all part of that same end goal, okay? So let's do some drawing here. My dad is pretty good at math, and when I was in high school and middle school, there were, he would help me out with my math homework and stuff like that. But there were definitely a lot of, there was also a lot of fighting, because doing math with your dad when you're however old is not always the thing you want to do. But I remember one time I didn't understand how to do a problem. And so my dad, English is not his first language. And so sometimes he says things in a way where it makes sense, but no one else would say it that way. And so he told me, he's like, well, if you don't understand the problem, just draw a bigger picture. And I was like, I mean, I guess I get what you're saying, but drawing a bigger picture isn't going to help. But it turns out that I find it actually very helpful when I don't really understand a pattern or I'm trying to find a pattern, that if I can draw a bunch of pictures, it helps me understand why we have certain rules, okay? So for example, I just told you, like, believe me, there's only 3 bumps at the maximum, or believe me, there's only 2 bumps in the maximum here. But I think some of us, and I hope some of us, are like, but why? Like, how does she know that? Okay, so let's kind of put that together in some pictures. All right, so let's do this in an organized fashion. I want us to start with a linear function. So tell me, how can I draw a linear function? What's a linear function look like? Yeah. Okay, yeah, I can draw a line, right? And so it could be the forward slash or the backslash, but effectively, those are sort of my options, right? I've got this one, or I could draw one that might be like this, right? We could also have a horizontal one and a vertical one, right? So we do actually have like 4 different options here. So I could also draw a horizontal line. My dad also told me that I can't be a real math teacher until I can draw like a perfect circle. I feel like he would be mortified at my my drawings here. But those are sort of our options for linear functions, okay? Now, when we're looking at these, how many times does the blue line cross the x-axis in this first diagram that I drew? Like, how many times does this blue line cross the x-axis? Once, right? It crosses right here. All right. What about this one with the negative slope? How many times does that cross it? Once. And that goes right there. What about this diagram? How many times does that cross the x-axis? None. Okay, so no x-intercepts. Okay. What about the last graph? How many times does this cross the x-axis? One. Okay. So can can we draw a line that crosses the x-axis more than one time? No, not really. Okay. I think we could think of one exception, which is maybe if the horizontal line is exactly the same as the x-axis. That might be our one exception. But in general, when we draw these, we can only have one x-intercept. Now check this out. What's the degree of a linear function? It's going to be first degree, second degree, third degree. It's going to be first degree. Okay, so a linear function is first degree. And it can have at most one x-intercept. How many bumps does a linear function have? None. Okay, does that fit with our rule before? The degree minus 1 tells us the most number of bumps that's going to happen. It does, right? 1 minus 0, or 1 minus 1 is 0. So at most 1 x-intercept and 0, let's use extrema. okay? Now, we're talking about end behavior here. So if I look at the end behavior, I really want to let's focus on these two and not on our sort of special cases. But my options for end behavior, I could have down and then up. So the left end goes down and the right end goes up. Or the left end goes up and the right end goes down. Okay, so those are sort of my options here. Let's shift gears a little bit and talk about the quadratic function. Okay. We know quadratic is second degree, x squared. So how many extrema do you expect from a quadratic at most? One. Okay, 2 minus 1 gives us 1. So 1 extrema at most. Okay, so let's draw a couple pictures here. Okay. If I were to draw a parabola, I could draw a parabola that crosses the x-axis one time, or sorry, 2 times, like maybe something that looks like this. And it would cross like here and here. Does this parabola only have one bump? Right? It just has one bump. That's it. No more bumps. How could I draw a parabola that does not cross the x-axis? Okay, shift it up above the x-axis. Good. So if I drew one that was like this, okay, I think we can see that that one doesn't cross the x-axis at all. So this one has 2 x-intercepts. This one has no x-intercept. Can we draw a parabola that only has 1 x-intercept? And if so, what does that look like? We're not doing sideways ones, only ones that are facing up and down. Okay, good thinking. It has to only have a shift left or right. Okay, good, good. So if I take the regular parabola that has a center, as the vertex at the origin, and let's say I just moved it to the left like this. This has 1 x-intercept. Okay. So remember how for the linear I said, hey, at most we can have 1 x-intercept. But now we're at a second degree, and at most we could have 2 x-intercepts. We can't have a parabola that crosses 3 times because then it wouldn't be a parabola anymore. Okay, so we have 1 extrema, but we also have max of 2 x-intercepts. Okay, now my end behavior for these, I have up on the left, up on the right. up on the left, up on the right, up on the left, up on the right. Is that the only kind of end behavior I can get from a parabola? Okay. What other options do I have? Okay. Can you have a parabola that is up on one end and down on the other end? No, that wouldn't be a parabola, right? Yeah, Hillary, it would definitely not be a parabola. So we have our up option, and I won't draw it for all of them, maybe just for this first one here. We could also have sort of a down situation. Okay, it still only has two x-intercepts, but it's down and down. Okay. Now, it turns out that for quadratics, one of the important things that makes it different from a linear function is that the end behaviors for linear functions are opposite each other. Like if one end goes up, the other end goes down. But if we look at a quadratic, they have to match. The end behaviors have to match, okay? So either they're both up or they're both down. And exactly, okay? So Richard says, if the degree is even, the end behavior is the same. And if it's odd, the end behavior is opposite, okay? So that is exactly what we're gonna take a look at right here. Now, I just wanna do the cubic function to take a look at that. That is one of our sort of like common parent functions. So it's kind of nice to go over that. This is like the worst organization. Okay, so if we have a cubic, that means we have a third degree. Okay. Now, what's the maximum number of extrema for a third degree? 2. Good. 3 minus 1 is 2. So maximum of 2 extrema. And what's the most number of times we can have an x-intercept for a cubic? 3. Good. Okay. So max of 3 x-intercepts. Do we anticipate that this function will have matching end behavior or opposite end behavior? Yeah, it's going to be opposite, okay? And it's going to be opposite because that degree is odd, okay? So let's take a look at some options. Can I draw a cubic that crosses the x-axis 3 times? And that's going to look pretty similar to example number 10 from earlier, but it might look something like this. Okay. And we can see from here that it crosses here and here and here, right? So we've got 3 x-intercepts. How do I modify this diagram so I only have 2 x-intercepts? Okay, now, yep, I could shift it up or down. And so we could shift it. Let's say we shifted it down. Maybe what we want to make sure is that maximum just touches the graph and then it bounces back and then it crosses again here. Okay, So this is one x-intercept. That's not one. This is the second x-intercept. Okay. If I kept moving this graph down, I could actually get a cubic that only has one x-intercept. Okay. Now here's the challenge. How do I draw a cubic function that has no x-intercepts? Yeah, exactly, right? We can't move it far enough up or far enough down so that it does not cross. Now, I've had some students in the past who've been like, Judy, if you just draw like a really small one, like that one doesn't cross. And like, yeah, the way you drew it, it doesn't cross, but this extends forever and ever. Like at some point, it's going to cross, okay? So actually, we cannot have, so it's not possible to have 0 x-intercepts. Okay, it's not possible to have 0 x-intercepts. This one is not possible. Now let's just double check. For all of these, I had 2 bumps, like a maximum and a minimum. But sometimes you might actually see, like, let me modify this one x-intercept graph a little bit. You might actually see that it sort of like flattens out and then goes up. So it depends on what goes into the equation. You might have no bumps, and that's okay too. All right. So a maximum of 3, but we can't have more than 3 of 2 turning points. Okay. Now let's look at our end behavior. They're all opposite, right? This one is down, so that side has to be up. This one is down, and that one is up. This one is down, and that one is up. And I could switch them sort of the same way I did with the quadratic by putting a negative sign in front. And then it would have the end behavior of up on the left and down on the right. Okay. So let's fill in a little chart, which should look fairly familiar to you if you've seen end behavior before. But when we look at end behavior, if we want to know right away from the equation, these are the things we need to look at. We need to look at something called the degree. Okay, so the degree of the polynomial, we need to know that. If we have an odd degree, that's going to be one case. And the other case for that is you might have an even degree. So because we're working with whole numbers, all of our degrees are going to be even or they're going to be odd. And then we want to look at the sign of the leading coefficient. So that's why we practiced earlier finding the leading coefficient. So whether that sign is positive or negative is going to impact our end behavior. So if we have a positive sign of the leading coefficient versus if we have a negative sign of the leading coefficient, okay? And so those 4 cases are gonna help us remember things that happen for all odd degrees and all even degrees. So if you have an odd degree and you have a positive leading coefficient, that's gonna be like this guy right here. And so that end behavior, we read it from left to right, and on the left it's down, and on the right it's up. So all we do is we say this, down, up. Those arrows show that they're opposite. And the left arrow shows the left end behavior, and the right arrow shows the right end behavior. If I have a negative sign for the leading coefficient and its odd degree, that's going to be like this second case right here. So we're going to say down, up. Sorry, up, down. Okay. So odd degree, the end behaviors do the opposite of each other. And even degrees, they match. And we can think just to the quadratic case. If it's positive, then it's going to be up, up. And if it's a negative leading coefficient, it will be down, down. Okay. So as you're maybe preparing your reference sheet after class today, I think this table is really helpful to have on there. You might not need to have all these other little diagrams that we talked about earlier, but I do think they help you remember sort of like why things are the way they are, okay? Okay, so let's do this. I want to go over example 13, and then we're going to take a break. And after the break, we're going to come back and I'll send you into some breakout rooms to take a look at the other examples. Okay, so let's do example 13. We'll take a break and then we'll have some time to practice in small groups when we come back. So for example 13, here's what I want. I'm telling you that there's a polynomial that's in factored form and it's in the third degree. So that's the information that I've given you here. And I would like you to find out what's the end behavior, what's the maximum number of extrema, what's the maximum number of x-intercepts, and then I want you to write a polynomial that matches those pieces of information, okay? So let's see, what can we fill out just by knowing the degree here? Okay, so Thea says the maximum of extrema and x-intercepts. So the maximum number of extrema is going to be 3 minus 1, or you're going to have 2 bumps at most, okay? What about the maximum number of x-intercepts? How many times can a cubic function cross the x-axis? Yeah, that's going to be the same as degree, okay? So this one is the same as the degree. And this one is the degree minus 1. Wow. Okay. All right. What about the end behavior? Do we know the end behavior? No. Okay. But I think we know some options, right? I think we know it's not going to be up, up, and it's not going to be down, down. So let's actually write 2 possible answers here. So one possible answer is you have end behavior of down, up. And the other possible end behavior is it could be up, down. Right? You could have down, up, or you could have up, down. Now, if I wanted to write a polynomial that had an end behavior of down, up, and it was in factored form, I could write something like this. X minus 3, x plus 5, x minus 1. That's third degree, right? X times x times x will give me x cubed. And my leading coefficient is positive. How could I modify this to write a polynomial in factored form that had the opposite end behavior, up, down, instead of down, up? Put a -1 in front of that first term. Exactly. So check this out. If I write f of x equals negative x minus 3 times x plus 5 times x minus 1, this minus sign now makes it have that opposite end behavior. Okay? Now, where did I get these numbers 3, 5, and 1? I literally just made them up. Okay, so sometimes when I ask folks to write an equation, they panic and they're like, well, but like, what number am I supposed to write? You can write whatever numbers you want, okay? You could have even done something as simple as this. Or for the blue one, you could do something like this. So there's lots of options for how you write your polynomials, okay? You just have to make sure you've got the degree correct and that you've got the right form. If it's factored form, you got to write it in factored form. If it's standard form, you got to write it in standard form. Okay? Are there any questions on this first part of the lesson for today? Okay. So I'm going to go ahead and stop sharing the screen, and I'm going to